Everyone. So yeah, I'd like to talk about seismic instrumentation in LIGO and how first I'll talk a little bit about what are gravitational wave interferometers, what is LIGO, and what are our science goals. So kind of what's the more global point. I'll talk about why we need what we call seismic isolation. And then I'll go into how we use seismic instruments for seismic isolation in the LIGO interferometers. In this section, I'll also talk about a few other ways that we use seismic instruments in the LIGO interferometers. I'll briefly mention at the end some developments that are happening within the LIGO scientific collaboration on seismic instrumentation. And then I will look forward to questions. So first, what are gravitational waves? What is it that LIGO is trying to measure? In the upper right corner, I have a picture of a system of two black holes, and you can imagine them spiraling around each other, and they're getting closer and closer to each other with time. And when these black holes are spiraling around one another, they will actually cause space-time itself to stretch and squish. So if we have a gravitational wave coming from these two black holes, traveling kind of towards the lower left side of the screen, and we have these blue rings in space-time, the gravitational wave, what it's doing is it's stretching and squishing space-time, and we can see that stretching and squishing in these blue rings. So what we're trying to do with LIGO is we're trying to actually measure these distortions of space-time. We're trying to measure how space-time is changing as a gravitational wave passes through something like the Earth or a detector on the Earth. This is a quick movie of how gravitational wave interferometers work. They are based on a Michelson-Morley type interferometer. So we have a laser that shoots the light to a beam splitter in the middle. The light goes towards the end mirrors and comes back. So here the light is being split in half. Half of the light goes to one end mirror and half of the light goes to the other end mirror. It reflects off of each of those end mirrors and comes back to the beam splitter to be recombined. And the recombined light will either constructively interfere or constructively, it'll either constructively add or deconstructively add to either give us a light spot or a dark spot on the photodetector here on the right side of the screen. So as the end mirrors are moving relative to the central beam splitter, we're getting a bright, dark pattern on the photodetector. This means that the amount of light on the photodetector is informing us about how the end mirrors are moving or how the distance between the beam splitter and the end mirror is changing. And so if we imagine from the movie on the last slide that the beam splitter is in the center of one of those blue rings and the end mirrors are on the edges of that blue ring, then as space-time is being distorted, stretched and squished, these end mirrors are either coming closer or farther away to the beam splitter. And so we're getting either light or dark patterns on this photodetector on the right side of the screen. And so from measuring this light, we can infer how space-time is being distorted. And from that, we can actually back out and try and understand what was the source of those gravitational waves. Was it a set of black holes? Was it a set of neutron stars? Was it something else? So that's how we kind of do the fundamental measurement in LIGO. There are 3 kilometer scale gravitational wave interferometers currently operational in the world. I am based here at the LIGO Hanford Observatory in Red. We have a twin site in Louisiana, just east of Baton Rouge. And their hardware is basically identical to ours. We have what I sometimes call a cousin interferometer in Italy that is run by a French-Italian consortium. and their interferometer is slightly shorter than ours and slightly different hardware, but the operational philosophy is exactly the same. The LIGO interferometers are 4 kilometers long, so you can see these L shapes in the overhead photos. They're really pretty long. And so each of the arms of our interferometer are 4 kilometers long. In Italy, those arms are 3 kilometers long. So this on slide 6 is a set of all of the gravitational waves that LIGO and Virgo have detected thus far. The one in the top right corner we call GW, gravitational wave 150914. That was detected on September 14th of 2015. That's our first ever gravitational wave direct detection. And since then, so that was during our first observation run, which ran for several months. And then we came offline for a while to do some maintenance and upgrades. And then we did another observational run starting at the end of 2016, running through August of 2017. And you can see that the date stamps on many of the other gravitational waves on this slide are from that 2017 run. Most of the gravitational waves on this slide are coming from a pair of black holes spiraling around each other and finally colliding. So if you look, each individual box the background is a time frequency plot. So the x-axis is time, the y-axis is frequency, and then the color, the intensity of the color is how much energy is there in the signal. And then overlaid is the time series of the signal. And in all of these, you can see more or less clearly that as a function of time, the amount of energy increases and the frequency increases. So we kind of call these a chirp because they start at modest frequency and then increase in frequency. And you can see on the time axes for most of these plots that they happen quite quickly. They're over in under a fraction of a second. That's because these black holes are quite heavy, and so they merge, they crash into each other at a lower frequency, and so they're detectable in our interferometer for a shorter amount of time. In contrast, the bottom right panel labeled GW170817 binary neutron star, that is a pair of two stars, two neutron stars that are spiraling around each other and crashing into each other. You'll notice first that the time axis is much, much longer. Because these objects are lighter, they merge at a higher frequency, and so we can detect their signal in our interferometer for longer. And so that's why we have more of the signal available to us to display. The binary neutron star merger, which happened near the end of our last run on August 17th, has been really exciting, and I hope that even if you don't follow LIGO, you've at least heard of it or are familiar with it, because this is the first gravitational wave detection that we've made that astronomers from other types of astronomy can look into the sky and also see something from this collision of two stars. For the collision of binary black holes, two black holes crashing into each other, we do not expect any material to come out of that. We don't expect any electromagnetic radiation to come out of that. However, for the collision of two stars, we do expect a lot of material and interesting electromagnetic information to come out of that. And so this object is now one of the most studied objects outside of our solar system, just because it's so interesting and so new. And we're very much looking forward to being able to detect more and more of these binary neutron stars in our upcoming observing run, which will hopefully start sometime in the next few months. This is really quickly just another view of the neutron star collision. Again, the time frequency plot in the top corner This time, the time 0 is at the actual moment of collision. And in the bottom left corner, there are two images, a before and an after image. And you can see kind of where the red arrow is indicating that after, in the evening of August 17th, 2017, the SWOPE telescope was able to see that there was a new object in the sky. This little speck where the red arrow is pointing did not exist and was not observable before then, but this is the aftermath of that neutron star collision. So it's really exciting that we are finally able to be sensitive enough to detect these kinds of things. And something that I'll come back to later is that the lower in frequency we are able to detect these objects, the sooner we can tell our astronomical partners that there's potentially a candidate in the sky that they could go look at. And in order to go to these lower frequencies, we need to leverage all of our ability to isolate ourselves from ground motion. So that's kind of the core of our seismic isolation needs. On slide 8 here, I have, as a function of frequency and displacement, the sensitivity of the LIGO gravitational wave interferometers. So the y-axis is how much are the mirrors moving in meters. The dotted lines are from our last science run of the initial LIGO era. So that is a first generation set of hardware. And you can see then that the solid traces down lower in labeled H1 and L1 2017, we've made a lot of improvement in our sensitivity over a very wide frequency band. And this is approximately what our sensitivity was during the time of that binary neutron star merger. Something that is interesting to note is that these really are meters on the y-axis. So our mirrors measured at 100 hertz are moving less than 10 to the minus 19 meters. This is less than 1,000th the diameter of a proton, and that's the sensitivity to which we are measuring our mirrors' motion. I should have noted in this plot that the red traces are the Hanford interferometer, H1, and the blue traces are the Livingston LIGO interferometer, L1. So one of the things is, how do we actually achieve this very, very precise sensitivity? And part of that is, how did we make such a major improvement from our initial LIGO era ending in 2010 up through our current advanced LIGO era now? And a lot of that, particularly at low frequencies, is a result of our new seismic isolation, our upgraded seismic isolation system. So on this slide, you can see kind of a first big picture overview of our seismic isolation system. The kind of flat gray panel at the very bottom represents our instrument floor. These blue piers sit on the instrument floor. At the top of the blue piers are some hydraulic actuators that have co-located geophones in them. And we isolate such that the top of these piers are moving about 10 to the minus, or sorry, 4 times 10 to the minus 10 meters per root hertz measured at 10 hertz. Then the table, the light silver, is sitting inside of the larger kind of cylindrical vacuum chamber. And the light silver table is suspended entirely on this blue pier system. So the dark gray vacuum enclosure, cylindrical vacuum enclosure, is sitting on the floor, but the light silver table is not actually physically connected to that outside vacuum enclosure. It's sitting entirely on this blue pier system. And this seismic isolation table, which I'll go into more detail in a slide or two, isolates another few orders of magnitude so that now we're moving about 10 to the minus 12 meters per root hertz at 12 hertz. From that seismic isolation table in pinkish purple, we have our mirrors themselves. The mirrors are suspended as a set of 4 pendula hanging in series from one another. And then at the very bottom of that pendulum is where the laser is actually going and bouncing around. And that's where we're actually measuring the motion of the mirrors to understand what the gravitational wave is doing as it passes by. This is kind of a zoom in of the quadruple suspension for the mirror. It is almost entirely passive vibration isolation. We utilize the fact that a pendulum is a natural mechanical vibration isolator to help isolate it from ground motion, whereas the blue and light silver system in the right picture, those are a lot more active seismic isolation coupled with some passive seismic isolation. In the quadruple pendulum picture on the left side of the screen, at the very top we have what we call blade springs. So these are what are actually attached to the table. They're hanging from the table. And they give us a little bit of vertical isolation. So if the table is moving in the z-axis, this gives us some pendulum-like isolation in that direction. And then from those blade springs are hanging the series of pendula. And then at the very bottom is the mirror itself, moving at about 10 to the minus 19 meters per root hertz, near 10 hertz. Yes. So here we have kind of schematic-ified drawing of going back to the seismic isolation system that kind of helps hold and support the mirror pendula. So in the blue, again, we have the external pre-isolation system, which uses hydraulic actuators. These are quite high range for us. They can move about plus or minus 1 millimeter in each axis. They're 6-axis actuators, so they can do kind of anything we need. And then the gray system we call our internal seismic isolation because it's internal to the vacuum system. And then from, in this schematic drawing, the top part of the table is suspended the actual quadruple pendulum and mirror system. So if we zoom in a little bit to talk about the hydraulic pre-isolation system, it is kind of on the one hand sophisticated, on the other hand kind of simple system. It's got springs in purple to kind of hold it up. And then kind of the most important part is these feedback instruments, the geophones, as well as just relative sensors to tell us where is the hydraulic isolator relative to the ground motion. We also use a ground seismometer, usually either a T240 or an STS2, to help us understand how the ground is moving, because we don't necessarily always want to hold the top of the isolation system still relative to itself. We want to isolate it from ground motion. So we feed forward some of this ground instrument and blend that into the control system for the HEPI, this hydraulic pre-isolator. And then connecting each of these, there's 4 of these pre-isolators per table. So connecting them are these support tubes that here are drawn in red. And then the table, the internal seismic isolation table, sits on those support tubes that connect the 4 HEPI pre-isolators together. On the next page, we can zoom in separately to our internal seismic isolation system. This is where we get a lot of our more fine-tuned isolation from ground motion. So this is nested inside one another, actually 2 stages of isolation. It's got several different co-located seismic instruments on board. So near the kind of more edges, we've got GS13s. We also have L4C geophones on board. And then at the kind of core, at our most sensitive location, we have a T240 broadband seismometer. We also have local sensors just to tell us where is each stage of isolation table relative to each other stage of isolation table. And these sensors are blended together in a frequency-dependent way. And then we actuate using voice coils to hold the table still. And often, again, something that we will want to do is either make a choice between holding the table still and isolated from ground motion local to itself, or sometimes we want to measure the difference in ground motion between the beam splitter and our end mirrors and make the difference in ground motion not appear at the tops of our tables. But all of this different instrumentation allows us to have that flexibility. This is a plot of just the performance of our seismic isolation tables. You can see in the dashed line the requirements that we believe that LIGO needs for our tables. And then also plotted just for reference in kind of smaller dots is the noise limit of a GS13 as an example geophone. In gray and black, we have seismometer information on the ground next to one of our tables. And then in red and blue are the actual measured motion on board on the most isolated portion of our table. And you can see that we have several orders of magnitude isolation from ground motion at 10 Hertz. And that at almost all frequencies, we are more isolated than we require, which is really good and really helpful. This is just the tables. So the quadruple pendulum system is suspended from these tables. And so we get even more isolation from ground motion above the pendulum resonances, which are around 1 Hertz. So this combination of the isolation table and the pendulum system gives us this exquisite total vibration isolation above 10 Hertz. We have other noise sources in LIGO, but without the seismic isolation system, we wouldn't be able to control the locations of our mirrors nearly precisely enough to even see any of these other noise sources. So this seismic isolation system is really critical to the entire operation of LIGO. Something that's kind of interesting and I don't think we really appreciated until later, and certainly have had to deal with much more recently, is the tilt coupling effect in our ground sensors. Our ground seismometers are used, as I mentioned, to blend into the seismic isolation platforms to help us isolate even further from ground motion. However, as you are likely aware, the seismometers cannot distinguish at low frequency the difference between true horizontal motion and tilt motion. If we think of a seismometer as a mass on a spring, if there's true horizontal motion, the mass will move back and forth on the spring, and then we'll be able to sense that mass's motion, and we'll call that horizontal motion. However, in a gravitational field, like on the Earth, if the seismometer is instead tilting, then the mass will still extend or detract the spring. So the mass will still look like it's moving, but instead of being moving due to true horizontal motion, it's moving due to the seismometer being tilted. But the seismometer doesn't know that, and so it reads it out as true horizontal motion. Since we use the seismometers, then we are actually injecting this tilt motion into our seismic isolation platforms. And so we're trying to isolate against horizontal ground motion, but there's some tilt motion that's being read as horizontal motion. And so the extra tilt component is noise that we're injecting onto our tables, which is undesirable. We get tilt from really the wind pushing on the walls of our building. The walls are connected to the floor, and this wind pushing on the walls of the building is tilting the instrument floor, the slab, the big concrete slab that all of our tables, all of our geophones, all of our seismometers sit on. Everything sits on the instrument floor slab. And so when the wind is blowing hard enough, in excess of 30 or 40 miles per hour, then it's a very significantly noticeable effect on our interferometer. So what we have done is we can now independently measure the tilt of the ground. We correct the seismic sensor that's on the ground for that tilt motion, and then we use the super sensor as our actual horizontal motion sensor that we then use for actuating on our tables. So in the plot here, as a function of frequency versus acceleration, in blue, you can see a measurement of ground motion from a T240. You can see also in orange the information from a tilt sensor that has been developed at the University of Washington. And if you subtract those two, then you get this yellow dotted dashed curve. And so you can see that the true horizontal motion is really much less than the T240 is natively reading out. And so that's almost an order of magnitude of noise that we would have been injecting into our seismic isolation tables that now we don't have to because we have these independent tilt measurement devices. And then the purple trace is just the noise readout limit of this beam rotation sensor, this tilt meter. But having the external tilt sensor has really made it so that we can operate our interferometers in more windy times, which particularly here in Eastern Washington can be a significant fraction of the year. So this wind coupling through the tilt, through the seismic system, sometimes would prevent us from having control of the interferometer at all, so we could not be in scientific observation mode, or at the very least would cause noise, and so our sensitivity would be degraded a little bit. Here on the next slide is just a quick cartoon of how the beam rotation sensor works. It sits on the floor, and then the beam rotation sensor itself is holding still in an inertial reference frame where the ground rotates, and then you just can measure this angle between the inertially isolated beam rotation sensor and the ground and get a good estimate of how the ground is tilting independent of any horizontal motion. Another thing that's a real big problem for us in LIGO is earthquakes. Earthquakes, as I'm sure you in this community are well aware, cause ground vibration that can be sensed all around the world. So something that we have tried to work on is there a way that we can change our seismic isolation platforms to be more robust against an incoming earthquake? Usually we operate all of our control systems, including our seismic isolation platforms, in a very, very high sensitivity state, but that has a limited actuation range. So if the ground is going to move just with too much velocity at some set of frequencies, we don't have the actuation range to hold the table still, no matter what the ground is doing. But we think that we can loosen up on our control systems potentially and give ourselves a little bit more actuation range at the cost of high precision in order to keep the interferometer under control during an earthquake. Something that part of the key here is that if we lose control of the interferometer due to an earthquake or something, it can take between 20 minutes and an hour to bring ourselves back into scientific observation mode. So if we can transition out of scientific observation mode to a still controlled but just less sensitive mode, then we would be able to, once the earthquake had passed, immediately transition back to our scientific observation mode in a matter of 1 or 2 minutes, rather than tens of minutes. So this plot is a collection of data from many, many just times of the interferometer when an earthquake has passed, and plotted as a function of the ground velocity. In red are times when the interferometer lost lock, we lost control of the mirrors. And in blue is times that we were able to hold on to control of the mirrors. So you can kind of see that if the velocity doesn't get too high, then we're more likely to be able to hold control of the interferometer. But something that we're working towards is to push this velocity even higher. One of the things that requires, though, is some kind of advance notice that the vibrations from an earthquake are coming our way. So we pull the USGS earthquake alerts and have functions to tell us, based on the location, magnitude, and depth of the earthquake as reported by USGS, what is the predicted amplitude of the ground vibration and what time are we expecting the SP and R waves to arrive. Usually only the R waves are the ones that really cause us to lose control of the interferometer, but occasionally for larger earthquakes, S and P waves can cause problems. But if we are able to know when an earthquake is expected, then we can move ourselves to this more robust mode of operation, and then once the earthquake passes, move back to our more sensitive mode of operation. So this is an active area of research that we're working on. One of the other really big ways that we use seismic sensors is to validate our gravitational wave candidate events. The plot in the upper right is another plot, time frequency plot of our first ever gravitational wave detection for both the Hanford and Livingston interferometers. And so we can see our classic, as expected by general relativity, chirp in the time frequency plane. And then we can look at all of our several 100,000 auxiliary channels and confirm that we don't see anything of that shape in any of our other signals. For this particular event, there was a seismometer that saw some ground vibration during the time of that gravitational wave event. So then we can look at the time frequency plot of that seismometer signal and see that it doesn't look anything at all like a gravitational wave signal. It lasts much longer, many, many tens of seconds longer than the gravitational wave itself, which is lasting a few tens of milliseconds. Also, none of these seismic signals, the kind of bright streaks in the seismic plot, none of those are increasing in frequency as a function of time. So they don't look anything like a gravitational wave would be expected to look. So we can say that this seismic signal, which turns out to have been an air compressor that comes on occasionally, is totally unrelated to this gravitational wave candidate event. And so we do not need to exclude the gravitational wave candidate event. Something like this air compressor, we can see that it comes on and off all the time, and we do not see candidate gravitational wave events like this at every single one of those times. So this kind of looking at our auxiliary sensors, particularly including all of our seismic instrumentation, can help us ensure that a gravitational wave candidate event is of true astrophysical origin and not due to some kind of anthropogenic something, either ground motion or some kind of electronics glitch or something. For this first ever gravitational wave detection, we looked at all of our magnetometer signals because there was a lightning strike in Africa. So we're really trying to do our best to ensure that nothing on the Earth could have caused this gravitational wave candidate. And that includes going in very fine detail through all of our seismic ground vibration sensors to understand and make sure that there's nothing on the ground that could have coupled into the interferometer and looked like a gravitational wave. Once we can say that our interferometer is online because we have a good seismic isolation system and we think we're sensitive to gravitational waves and we're doing great, we can ask, how can we use the seismic instrumentation to make our sensitivity to gravitational waves even better, even more precise? So this is actually a plot from 2010, well before we ever directly detected gravitational waves, but at a time that we did have gravitational wave interferometers operational in our initial phase. And here I'm using feed forward of the seismic signal, the difference between the beam splitter area and the end mirrors. And I'm using the difference in that ground motion to feed forward online to reduce the difference in mirror motion between the beam splitter and the end mirrors. So in black is a trace of how much our mirrors, something related to how much our mirrors are moving without this feed forward system enabled. And then the red traces are with this seismic feed forward system enabled. And you'll see that particularly around the microseism, I've made some improvement. We've reduced the motion between the mirrors. There is a sacrifice at around 2 Hertz or so, well, above 1 Hertz, actually almost all the way to 5 or 8 Hertz here. But because that area will be cut off, will be isolated by the pendula, we kind of let that go and we accept that as a first demonstration of the system because we care more about the microseism. When our mirrors are moving so very much due to the microseism, we can get nonlinear upconversion of noise sources at much higher frequencies, with those higher frequencies interacting with the mirror motions at the microseism. So things like our 60 Hertz power mains, those are electronics. We all operate in the US on the 60 Hertz power. And so most of our electronics do see a sharp feature at 60 Hertz. And so we exclude data right around 60 Hertz in many of our gravitational wave searches. But if that 60 Hertz line is somehow nonlinearly upconverted against the microseism, then that broadens the 60 hertz line. So now instead of being, say, precisely 60 hertz, it's a line plus and minus the microseism around 60 hertz. And so now we have a wider set of frequencies that we must exclude from our gravitational wave searches. So to be able to reduce the motion at the microseism, even by a small amount, is a big win, and we allow this slight extra motion at higher frequencies because the overall mirror motion is less at those higher frequencies than it is right here at the microseism. Yet another noise source that we need to be concerned about in LIGO is Newtonian gravitational noise due to some mass being in the vicinity of our mirrors, our pendula. And it really is just g/mm/r squared gravitational force. So if the mass is there, there's some gravitational attraction. And then if the mass is gone, then the gravitational force will be less and the mirror will swing closer to neutral. This is just a plot showing in blue the sensitivity, the expected sensitivity of the advanced LIGO detectors once we hit our full sensitivity limit. In brown is an estimated sensitivity curve for some future generations of LIGO-like interferometers. And the other traces are all estimates of the Newtonian noise contribution from various noise sources. And the summary of this plot is that for advanced LIGO's sensitivity, Newtonian gravitational noise from ground vibrations underneath our test masses can actually be a noise limitation for advanced LIGO. Also that none of these other potential sources like the tilt of buildings or infrasound inside the buildings is going to be relevant for our current interferometers, although will certainly be more relevant for future generations of gravitational wave interferometers. So one way that we are looking at what can we do to measure and reduce the effect of this Newtonian gravitational noise is I have had during a previous observing run here at the Hanford Observatory an array of 30 L4Cs placed on the floor in our main instrument hall, kind of near the bottom lefty-ish portion of the figure is our main beam splitter. The laser is coming in from the left, and our photodiode that measures gravitational waves is kind of at the bottom of the figure, off the figure. And the laser beams actually go off the top and left of the figure for several kilometers. But these geophones are arrayed kind of few meter spacing, and also co-located near the center of the array is one of these beam rotation tilt meters. So the goal of this array is to measure the seismic fields that are present as a function of time in our actual facility and try to understand a realistic ability to subtract this Newtonian gravitational noise from our interferometer signals. So we can do several things like generate KF maps to try and see what the seismic waves actually look like as a function of time, and then extract from the KF maps the seismic speed. And you can see that for the most part, we don't have a lot of dispersion in our facility. And this suggests to us that surface Rayleigh waves are the dominant source of ground vibration right under our mirrors. And that was an important discovery for us because it implies that we only need vertical geophones and that we do not need to bury any seismic sensors under the ground. If we saw a lot of dispersion or higher seismic speeds, higher effective horizontal speeds, that would imply to us that we had more seismic vibration from body waves, and that in order to do Newtonian noise isolation in post-processing, we would have to bury seismic instruments, a whole array of seismic instruments. So this was an important test to help show that we do not, in fact, need to do that burial of instrumentation and can just utilize instruments on the surface. We can also use the tilt sensor as a proxy for Newtonian noise and do some optimal filtering to try and understand how well we can actually use the array of seismometers to subtract the expected gravitational noise from the tilt sensor, our proxy. And it looks like right now in our current facility, without trying very hard, we can subtract that Newtonian gravitational noise by a factor of 10, which is plenty for our current generation of interferometers. Although we do need to do more work for future generations of gravitational wave interferometers. Kind of a last thing is that we've talked about how the tilt meter has been very important for the operation of LIGO measured on the ground. Something that we are looking forward to doing, hopefully sometime in the future, is also measuring the tilt of our actual seismic isolation platforms. So this is a 6-dimensional inertial sensor that's being developed inside the LIGO collaboration, primarily at the University of Birmingham in the UK. And it is designed to live inside of the main vacuum enclosure and suspended from our actual seismic isolation platform. So in this figure noted as isolated platform. So this inertial sensor should be able to help us isolate our tables, give us even more precise measurements, and isolate our tables even further from ground motion and any tilt motion that could couple in through the imperfect system. So even if we think that we're not creating any tilt in, say, the hydraulic system or on our tables, through imperfections in the system, we may still see tilt. And so this will allow us to measure that tilt in situ inside the vacuum system. And you can see that in the figure on the right that we expect this to be more sensitive than even an STS-2 Streckheisen seismometer. And so we're hopeful that if we can actually make these and stick them in our vacuum system, that we'll be able to make our tables even more quiet, which will enable the sensitivity of the interferometer at low frequency to be even better, which will then allow us to detect gravitational waves sooner and tell our astronomical partners where in the sky to point even sooner. And so that's part of the real excitement about pushing towards lower and lower frequencies. So kind of a sum up, we've successfully measured gravitational waves resulting from objects such as black holes and neutron stars. And I hope I've described, at least in brief, a wide variety of the way that we use different seismic instrumentation and how they're all critical to the operation of the LIGO interferometers, from being able to observe for gravitational waves at all, through validating that a candidate event is of true astrophysical origin, and even future, what can we do to help make our gravitational wave sensors even more sensitive in the future. So with that, thank you very much. And just because this is recorded, the reference slides are here so that you're invited to look up more details about any of these different pieces. So thank you very much.
Great. Thank you so much, Jenny. So we do have some questions that were written in. Bill Harbert asks, have you turned the high resolution with respect to time and frequency content, seismic isolation into a virtual seismograph? Are 3D records of ground motion needed for isolation shared with IRIS in any form? This would be related to real-time motion of the seismic isolation table, for example, and otherwise just fascinating talk.
Thank you. So we don't do a lot of, let me see if I can parse and
sure, you need me to
have
read
this
things. Like, don't hesitate.
We don't really display things in 3D. We don't really display any 3D version of our seismic information, although we do use all of the axes of seismic information for our isolation platforms. Some of our data is shared with IRIS, but I don't think all of it is, although particularly after the IRIS Seismic Instrumentation Symposium last year, we're initiating some collaboration with some seismologists and geologists that I'm connected with there to try and get them some of our data so that they can use some of our data for their studies. Does that kind of answer most of the question?
I think so. Bill, you can weigh in. Um, Brandon Christensen asks, does LIGO use the same kind of 4.5 hertz geophones as you would find in like a Raspberry Shake, like personal seismograph?
Primarily what we use, I think, are the instruments that I've mentioned. We use the L4Cs and then GS13s, Streckheisen STS2s, and Trillium T240s. And then we also use several Wilcoxon accelerometers. So all of these are kind of at the scale of the size of your fist or larger. So none of them are really portable, like walk around with your cell phone or a Raspberry Pi size. I'm not actually familiar with a Raspberry Shake.
Okay. Great. Allison Bird asks, considering the potential for and history of strong earthquakes in the Washington region, is there a way to measure the weakening vibrations throughout your system after the earthquake passes to know when you can truly return to fully scientific observation?
We mostly for that, it's a very coarse thing. So there was an earthquake this morning. I think USGS reported it as 5.4 in El Salvador. I don't remember the depth on the top of my head, but we have just our ground seismometers displayed on our front wall so that we can watch the Earth's ground motion as it is here. And so I think this morning in our band limited RMS, we got to about 1 nanometer per second velocities. And then once it died down to kind of 0.1 nanometers per second, we started trying to get control of the interferometer back so that we could start. Right now, we're still in a maintenance and commissioning mode, so we're not actually observing for gravitational waves, but so that we could get back to that after about half an hour or so. We were at a low enough ground vibration level. But anyhow, I think the sum up is we use our ground seismometers and band limited RMS to try and give us a coarse empirical estimate of when we can go back to observational mode.
Great. Raj Mulek asks, PS Rayleigh wave arrival predictions can vary up to tens of seconds based on assumptions about Earth structure. Has LIGO incorporated constraints from reference Earth models obtained using three-dimensional seismic tomography, which are known to provide accurate estimates of such arrivals?
So that's a great question. And that's something that we are working on. In the past, our earthquake arrival estimator was based on a pretty naive Earth model. And we could see that, our expected arrival times were off by quite a lot. And so we've started to incorporate more sophisticated Earth models and have gotten better. But that's one of the areas of active improvement is to incorporate more and more of those Earth models to try and understand more precisely when an earthquake is going to hit us.
Great. John Orcutt at UCSD, they said that they operate he says they operate a triaxial laser strain meter at Pinion Flat and that it started collecting data in 1970. The system continues to run. Interferometry is used to measure the strain, and unlike LIGO, they hope to measure Earth motion accurately. So it seems like in the 70s, a few faculty at Caltech did visit Pinion Flat to see how it worked. And I guess that's what eventually became LIGO. And so I think I'll send it to you, Jenny. I think it's pretty long, but
Okay.
it's just comments on kind of some of the history about this. So, yeah, and I think the bottom main comment that installing strain meters at LIGO sites might also help. So I don't know if that's a future thing or.
I don't know that it's something that we have actively planned, but it is something that we've started to look at a little bit, but it's not in our active development plans.
Okay, great. Carlos, I'm gonna butcher this, but Besserell or Becquerel, what determined the geographical location of the LIGO facilities?
That is mostly a really, it comes down to, in the end, a political decision. So we've recently gone through this again for our future LIGO India detector. We have the hardware for a third interferometer. And rather than placing a second one here at the Hanford facility, we're actually going to move it to India so that it's farther around the world so that we can get better astrophysical information from it. But the process is the same there as it was here in the 90s of look at typical year-round ground motion in a variety of different areas. Try and understand where in the country is seismically relatively quiet and can also offer a wide enough landscape that we can put a 4-kilometer L shape. And we also wanted it to be close to reasonable size airports so that we can have visiting scientists come and help us out regularly. So all of these kind of pull together a list of candidate sites. And then honestly, at the end, I believe that it came down to what senators from what states argued most effectively for having this scientific facility in their state. So in the end, Washington State and Louisiana won. I think the final political advocacy. But it starts out with ground measurements and trying
Sure.
to understand what's the quietest we can have.
Right. Tim Parker says, great work. Is there any references for the tilt meters? And it looks like there might be a couple that you put on these past pages, but I'll let you answer that.
Yes, particularly by Krishna, this very last one on slide 24 is the design document for the tilt sensor. And some of these others, like the third from the bottom by Michael Ross, Krishna's graduate student, is one of their early articles on using the tilt meter to do some seismology. So I hope that those references are helpful to you.
Great, thank you. Ken Anderson asks, will your 6D sensor designs be openly available, or is there a commercial vendor contributing to this?
At this time, it's not at a commercial stage yet. And to the best of my knowledge, the only designs that are openly available are the fourth from the bottom reference on this page by Connor Molowry and Den Martinov. At the time that I put these references together, they had submitted their article to PhysRev Letters, but the archive link is also there. So you can look at that, and then hopefully you can also use that to find any more information that they may have published since early last year.
Great. David Lumley asks that they are planning a large 1 to 2 square kilometer seismic array of broadband seismometers at the Australian G-Wave site at, oh gosh, Gingen, as well as a dense cluster in the detector building. And what lessons learned or suggestions do you have?
I've spoken with actually I had an email exchange with him just the other day, so hello.
Oh.
Let's see. I haven't thought very deeply about it yet because I've been working on the actual Hanford interferometer. I think just being able to have all of the data and get the data easily accessible will be really great. And then to be able to associate that with the Jenne interferometer data, I think will be really interesting. And I'm looking forward to seeing some results from that. But
Great.
maybe I don't have any immediate
Yeah.
suggestions.
Yeah, well, good. It's good to hear your pronunciation too. I did a hard G and you soft G. Eric Fielding asks, have you looked at the predicted motion from a magnitude 9 scenario earthquake, like on the Cascadia subduction zone? Would this motion be so large that it would cause permanent damage to the seismic isolation system?
Short answer is no. I don't know that we've looked at that. I think we're just hoping that it won't happen anytime soon. Also because it would be really hard on our cities and infrastructure, of course. We have safety systems in place so that our isolation platforms can't move outside of their typical range. However, there is some risk that for such a large earthquake, so very, very close, the mirror suspensions could break. So that's a risk. And we've done everything that we can to put safety systems in place so that the mirrors can't move so much that those fiber optics, the fiber suspensions that hold the last stage of mirror up would break. So we've got as many safety systems in place as we think we can, but there's always no telling when you have such a large earthquake, so very, very close.
Right. Bruce Bowden asks on behalf of the Pascal Instrument Center, do you have to isolate atmospheric effects as well, specifically related to like the chart figure you showed of the gravitational wave?
Atmospheric effects. Certainly not in the traditional astronomical telescope kind of way, because we're not directly looking at the sky. And so the gravitational wave signal that we're seeing basically passes through the Earth, passes through the atmosphere without any kind of distortion. Gravitational wave signals couple very, very weakly to matter, which is what makes them very, very difficult to detect. It takes something as big as a black hole spinning around as big as another black hole, and then it barely, barely moves our mirrors. So the gravitational wave is not really distorted by atmospheric effects in that way. However, if you look back at the Newtonian gravitational noise section, you'll see that in the future, we may need to consider the Newtonian gravitational effects of atmospheric noise. So just really the mass of the air moving around inside of the building can be enough of a gravitational force to affect the positions of our mirrors for future generations of gravitational wave interferometers. So those kinds of atmospheric effects we will absolutely need to take into account. And there's a lot of active research going on, particularly with our Italian and European colleagues, on looking into how can we do that for our next generation interferometers.
Great. Thank you so much, Jenny. So that's the end of our questions. And a lot of people afterwards wrote back in to say thank you for answering our questions and that you did an excellent job with the talk. So thank you all for attending Jenny's webinar today. Thank you for such an active Q&A session. And so with that, thank you so much for attending and have a great rest of your day. So take care, everyone.
Thanks. Bye-bye.
Bye. Bye.